Hello people, this is Guru and we are discussing compiler designing. In this particular video, we are going to study about finite automata. So let's start. Finite automata is a state machine that takes a string of symbols as input and changes its state accordingly. Finite automata is a recognizer for regular expressions. When a regular expression string is fed into finite automata, it changes its state for each literal. If the input string is successfully proceed and the automata reaches its final state, it is accepted. That is, the string just fed was said to be a valid token of the language in hand. So, the mathematical model of finite automata consists of finite set of state that is denoted by capital Q and finite set of input symbol that is denoted by summations. After that, one start state that is denoted by Q naught and set of final state that is denoted by QF and transition function that is denoted by delta. The transition function maps the finite set of state to a finite set of input symbol that is capital Q into summation tends to capital Q. Means that fa can be represented by a 5 tuples that is q, sigma, delta, q naught and f, where q is finite non-empty set of state, sigma is finite non-empty set of input alphabets, and delta is the transition function which maps q into sigma into q. Mapping is unusually represented by transition table or transition function, and q naught belongs to q is the initial state and f is subset of q is the set of finite state. Now that is necessary to understand finite automata constructions. So let R of L be a regular language recognized by some finite automata FA. State of FA are represented by circles and names are written inside circle. The state from where the automata start is known as the start state. A start state has an arrow pointed towards it, and intermediate state have at least two arrows, one pointing to and another pointing out from them. After that finite state, if the input string is successfully passed, the automata is expected to be in this state. Final state is represented by double circle. It may have odd number of arrow pointing to it and even number of arrow pointing out from it. The number of odd arrows are 1 greater than even. That is, odd is equal to even plus 1. Now the transition from one state to another state happens when a desired symbol in the input is found. Upon transition, automata can either move to the next state or stay in the same state. Movement from one state to another is shown as a directed arrow, where the arrow points to the dimension state. If automata stays on the same state, an arrow pointing from a state to itself is drawn. Let's take an example to understand it clearly. So we assume FA accepts any 3-digit binary value ending in digit 1. So here is the transition diagram of the FA which accepts 3-digit binary value ending in digit 1. Here initial state is denoted by Q0 and final state is denoted by QF. And final state is represented by double circles. Here start state has an arrow pointed towards it. So we know that binary numbers have two values, that is 0 and 1. And this transition diagram are giving any 3-digit binary value ending in digit 1, because when we put any 3-digit binary value, then when first value is 0, then Q0 take it, and when first value is 1, then Q0 gives it to final state. And according to the condition, we know that final state only takes those values which is only 1, and that is the ending value of 3-digit binary number. Then we can see here, when we put 1, then QF take it, otherwise it gives to Q0. So let us have more clarity on this particular topic, that is finite automata, through this particular example, that is example of lift control. Here we are taken very simple example. Let us suppose we are having 3 floors: ground floor, first floor and second floor, and that is one lift. This lift will move in between these floors. If the lift is at the ground floor, then we shall consider that the lift is at state Q0. In the first floor, then it will be treated as it is in the state Q1. And if the lift is found in the second floor, then we shall consider that this lift is at state Q2. And these are the input symbols, input alphabet, whatever it is. So here 0 means I want to go to the ground floor, and 1 means I want to go to the first floor, and 2 means I want to go to the second floor. So these are the input alphabets and input symbols. And this is the lifts. 3 floors are there, and respective we are having Q0 to Q2. Now let us consider this transition at first. So what is a transition system? It will be something like this. It is nothing but a directed graph. And here we are having notations like this circle will be denoting states, and rest we know. So let's understand the situation according to the condition of lift control on transition system. So here Q0 is initial state and Q2 is final state. Now see, at ground level, if you press 0, that means you will remain at ground, and if you press 2, you will go to the final floor, that is Q2, and if you press 1, then you shall go to the first floor. Then what are they? They are the inputs. And what are they are the directed edges, denoting the transition from one state to another state. Now if we are on a first floor and we press 1, then we remains on first floor, and when we press 2, then we shall go a second floor, and when we press 0, then we shall go on ground floor. Similarly, when we are on final floor, that is second floor, when we press 1, then we shall go on first floor, and when we press 0, then we shall go on ground floor, and when we press 2, then we remain on final floor. So very simple logic here. This is one kind of representation of finite automata, and the same thing can be represented by the transition table. So let's see how can I represent the same thing by transition table. So here we are having three states, that is Q0, Q1 and Q2. Q0 is initial state and Q2 is final state. We are putting inward arrow on Q0 because this is initial state and Q2 is final state. Then I am putting a circle, and these are the inputs, that is 0, 1 and 2, and these are the next steps. Here we can see Q0 with 0 input is Q0, and Q0 with 1 input is Q1, and Q0 with 2 input is Q2. Similarly, Q1 with 0 input is Q0, and Q1 is 1 input is Q1, and Q1 with 2 input is Q2, and similarly Q2 with input 0 is Q0, and Q2 with input 1 is Q1, and Q2 with input 2 with Q2. So now what is first one, that is Q. So Q contains Q0, Q1 and Q2. That is a finite non-empty set of states. And what is sigma? Sigma is finite non-empty set of input as alphabets. So what are the input symbols are there? 0, 1, 2. So I have written that one. And what is the next one? That is delta. We know that delta is a transition function, and we retain transition function here, that is Q0, 0. Then here what is Q0? Q0 is one of the member of capital Q. And what is 0? 0 is one of the members of sigma. So Q cross sigma means what? How many states are there? Q3. And how many inputs are there? So 3. So if you go for the condition product, then how many condition can we get? 3 cross 3 means 9. Then here is our 9 combination. So in this way I am having all these state conditions using by delta. So I am going to check delta Q0, 0 is 0. So let me check in transition table, delta Q0 with input 0 is Q0, and delta Q0, 1 is Q1. So here in transition table, Q1 with 1 is Q1. So in this way all this delta transition function we have written here. So what is the next one? Next one is Q0, and Q0 is initial state, and Q0 belongs to a capital Q. And what is the last one? That is set of final state. So what is my set of final state? So F is this one, and F is subset of capital Q. So in this way we can define a finite automata. That means if we know the logic how the system will work, then we can have this finite automata. Can be defined using 5 tuples. And what are they? There is Q, sigma, delta, Q0 and F. So for more detailed knowledge, watch our next video and please view with us.